Made of alloy steel, the cylinder resists the pressure of combustion and provides a working surface for the piston. The cylinders are usually secured to the crankcase by studs and nuts. One end of the cylinder is sealed by the cylinder head. The piston seals the other end. About 30% of the heat generated during combustion is transferred to the cylinders. Two cooling methods are used to maintain them at an optimum temperature. Liquid-cooled engines, like the Rolls-Royce Merlin shown here, have the cylinders contained in a jacket, which allows for the flow of a liquid around them. The liquid carries the heat to a radiator, like the one shown on this Mosquito bomber, where it is dispersed in the atmosphere. Air-cooled engines have fins machined onto the cylinders and cylinder head to increase their surface area. The fins are maintained in contact with the airflow, which is used to dissipate the heat. The cylinder head is generally made of aluminium alloy to improve heat dissipation. It seals one end of the cylinder to provide a combustion chamber for the mixture. On most modern engines, the cylinder head is screwed and heat shrunk onto the cylinder by the manufacturers. Some older engines, however, may have the head attached to the cylinder by means of studs or bolts. The cylinder head accommodates the valves and rocker assemblies. The valve operating mechanism generally consists of the valves, valve guides, valve seats, valve springs, rocker arms, push rods, tappets, and the camshaft. Inlet and exhaust valves open and close the passages for the induction and scavenging of the gases. The face of the valve is accurately machined to the same angle as the valve seat. The valve and seat are then lapped until a full contact is obtained. On very powerful piston engines, the exhaust valve stems are sometimes hollow and partially filled with sodium to assist in cooling. The valve guides guide the valve in a straight path and keep the valve concentric to its seat. The valve guide is usually pressed into the cylinder head. The valve seats are ground to form a gas-tight seal with the face of the valve. They are cut at various angles, for example 30 or, as in this case, 45 degrees. The valve springs are made of special spring steel to ensure that the valves remain closed except when they are opened by the cams on the camshaft. The springs are of the helical coil type, the usual practice being for two springs to be fitted to each valve, one inside the other. Having two springs fitted provides both a safety factor and also helps to eliminate the phenomenon commonly called valve bounce. The springs are held compressed between the cylinder head and the valve spring cap, the latter being located on the valve stem by split collets, which are located in grooves in the valve stem. The rocker arms provide a means of actuating the valves through a fulcrum, utilizing the camshaft, tappet, and push rod. The primary means of actuation is a single rocker arm per valve, mounted on a shaft in the cylinder head. The originating impulse which opens the valve comes from a camshaft or camshafts, which are driven by the crankshaft at half crankshaft speed. The camshaft rotates at half crankshaft speed because each valve is only required to open and close once per working cycle. That's to say, once for every 2 revolutions of the crankshaft. The angular position of the lobes on the camshaft of an aircraft engine is fixed, so that on an aircraft engine the amount of valve lead, valve lag and valve overlap remains constant, irrespective of changing engine speed. The fact that the camshaft is driven by the crankshaft means that valve opening and closing angles are referred to with respect to crankshaft rotation, not camshaft rotation. The sump is a casing attached to the base of the crankcase. It collects the lubricating oil after it's passed through the engine. In wet sump lubricating systems, we'll have more detail about these in the lesson on lubrication, the sump also acts as the oil reservoir, and all the oil is contained within it. In this particular engine, the induction system runs through the sump. The inlet manifold for each cylinder can be seen exiting the sump. The carburetor meters the air entering the engine and adds the required amount of fuel as a fine spray under all conditions of engine running. For an aircraft engine, the correct mixture must be supplied regardless of the altitude or the attitude of the aircraft. We'll be discussing carburetors in much more detail in Lesson 5 of piston engines on this CD-ROM. Some engines may have a fuel injection system fitted instead of a carburetor. Metal pipes connect the fuel control unit to a fuel manifold valve and thence to an injector for each of the cylinders. For the engine to operate, supporting systems are needed, and they will need power to drive them. Oil pumps, fuel pumps, superchargers and magneto-ignition systems may be fitted to the accessory housing and driven via gears by the crankshaft. The housing casing is fastened securely to the rear of the crankcase. It encloses the gear train and provides the mounting pads for the ancillary equipment. In some engines, a starter motor may be fitted to the housing. The accessory housing can also provide the drive to power aircraft systems such as electrical generation, hydraulics, and pneumatic systems. Lower-powered engines have the propeller connected directly onto the crankshaft. These are called direct drive engines. The most efficient speed of a propeller is comparatively low, as its tip speed must remain subsonic. Some engines may have to turn at very high rotational speeds in order that they can develop their full power. In circumstances where such an engine is used, to enable both the propeller and the engine to turn at their most efficient RPM, a reduction gear, such as the one shown here in this cutaway view, is used. The valves are continuously heated by combustion and expand at a greater rate than the rest of the operating mechanism. If there was no clearance between the valve tip and the rocker pad, then, as the valve expanded due to it being heated, it would no longer sit on its seat, and gas leakage would occur out of the cylinder. On older engine designs, to ensure that the valves close fully, it's necessary for there to be a valve or tappet clearance. This is a small gap measured between the rocker pad and the valve tip. As the engine heats up, the small gap or valve clearance shown here allows the valve to expand at its own rate. The valve clearance will become smaller as the engine gets hotter, but the valve still remains shut. The valve clearance is measured between the rocker pad and the valve tip by devices called feeler gauges, similar to the ones shown here, and in engines with this type of system there is provision made on the rocker arm for the clearance to be adjusted. Excessive valve clearance will cause the valve to open late and close early. On the other hand, too little clearance will have the opposite effect of causing the valves to open early and close late, and may even prevent the valves closing at all, thereby producing an event called popping back into the carburetor, which is where the flame of combustion in the cylinder is allowed to pass through the open inlet valve into the inlet manifold, and thence to the carburetor. The same effect can be caused by an inlet valve which is sticking in its guide. More modern designs of engines have hydraulic tappets incorporated. A hydraulic tappet is made in two main parts, one sliding within the other. Oil, which is supplied under pressure, causes the tappet to lengthen and take up any clearance when the engine is running. Thus, hydraulic tappets run with no valve clearance. They are pressurized using oil, which maintains contact throughout the valve operating mechanism and automatically adjusts for thermal expansion. Thus, valve operation is improved and tappet noise is reduced. Aircraft engines are classified by cylinder arrangement, type of drive, direction of rotation, cylinder capacity, cooling method, fuel system type, and whether they are supercharged, turbocharged, or normally aspirated. This engine is a Textron-Lycoming IO540. The I in the designation states that this engine is a fuel-injected engine. The O in the designation determines that it has a horizontally opposed cylinder arrangement. The 540 indicates the cylinder displacement of 540 cubic inches. This concludes the engine's general lesson.